Welcome to class AP Statistics. I am not here, but I really am here in voice and spirit and heart and mind and joy and hope and charity. Ah, how great that is. So let's see if I can teach you the lesson while I am lying on the beach sipping my diet cola. So today's lesson is our last lesson in this chapter. It's about the geometric distribution. But first, we'll do a little review, a little warm-up, as it were, based on the previous lesson. So find the new mean and standard deviations after transforming or combining the random variables x and y stated below. So the mean and standard deviation, you can imagine these as maybe the average on a test score for class X was 80, standard deviation 8, and the average on a test was 90 for class Y, standard deviation 3. I'll let you decide who is period 3 and who is period 4 between X and Y. So the first question, we have x minus 20. So hopefully you remember subtracting by a constant will change the mean. That would be 80 minus 20 is 60. However, adding or subtracting a constant to a random variable does not change the standard deviation, so the standard deviation would still be 8. The next one, we have multiply by a constant and then add 10. So for variable y, that would be half of 90 plus 10. The mean's affected by both operations. So that would be 45 plus 10 is 55. And the standard deviation is only affected by the multiplication of the constant, not adding a constant. So that would be 0.5 times 3 is the standard deviation of y. So that would be 1.5. is the new standard deviation. C, D, and E are based on our previous lesson. Now we're not adding or subtracting or multiplying by a constant like 20 or 0.5 or 10, but we're adding or subtracting random variables. So the difference in two random variables, the mean is simply the difference in the means. So if one mean was 80 and the other mean was 90, our new mean would be negative 10. So what this means in the context of test scores, if a randomly selected student was from this class and a randomly selected student was from this class, we would expect on average that the difference in their test scores would be a 10-point difference, where the class Y student would have a higher score and the class X student would have a lower score. So you can get a negative 10, just a 10-point difference between the averages. The standard deviations, and this was a new point on our lesson, these standard deviations, you cannot add or subtract standard deviations of random variables. You have to change them to variance. So to be able to combine these standard deviations, we would have to change it to variance, which is x squared is the variance, plus 3 squared. And then we're going to have to take a square root of that to make the units right. So that would be our new standard deviation. And feel free to correct me if I'm wrong, but when I do that, I get about 8.5. So that is our standard deviation for the difference of the random variable x and y. Now you might be uncomfortable, this little plus here. Anytime we're combining random variables, the variability of our transform variable increases. So the more random variables, the more variability that you have. So we're going to add here, even though it was a plus right here. See if you can do letter D. So pause this video and calculate the mean and standard deviation of D, as well as E. You might as well try both of those. And be careful because E are multiplying by constants. D is not the same as 3 times y. These are 3 separate random variables. So pause this video, see if you could do D and E. I see my initial screen may have had a slight difference. This is a 3y plus 2x on number E. Answer to that is not the bell that you're looking for. The answer to letter D is 240 for the mean and 5.2 for the standard deviation. The answer for E definitely is tricky when it comes to the standard deviation. The mean, I hope you got 430 for the mean. The standard deviation, however, you're multiplying by a constant. So the standard deviation will multiply by that constant. So it's 3 times the standard deviation would be 3. This one, 2 times x, the standard deviation 8 would be multiplied by the constant 2. However, to add them, to add the two, now we have to take this quantity and square it to make the variance, and this quantity and square it to make the variance, and then you add them, and then square root to fix the units. Definitely a tricky one on that, but the answer would be 18.36. And yes, I have seen questions on the multiple choice section and the free response section of the AP exam that are like letter E. So beware. I can always give you more practice problems in the future if you're confused about that. Now let us begin the new content, the last new content in this chapter about geometric probabilities. In the ever so popular game of Monopoly, which somehow my dad always wins, but I won't get into that right now, one way to get out of jail is to roll doubles. You could also pay $50, but who wants to do that? So suppose that a player has to stay in jail until he or she rolls doubles. So ignoring the rule that after the third time you have to pay $50, ignoring that rule, we're just going to leave him in jail, baby, until he or she rolls doubles. The probability of rolling doubles is 1/6. You just believe me on that. I won't take time to draw the sample space, but it's 1/6. Explain why this is not a binomial probability. This is not a binomial probability because you have no fixed number of trials. Fixed number, question mark? There is no fixed number. You're going to keep rolling until, that's a key word with these types of probabilities, you're going to keep rolling until you get doubles. You do have a constant probability of success, and die rolling are independent, and it's binary. It's either doubles or not doubles. But the problem is the n in bins. Good old bins. There is no n, no fixed number of trials. So it must be some other type of probability. Something else. So let's solve. For some reason, it's AA instead of A. But let's find the probability of AA. Probability that it takes exactly 3 rolls to get out of jail. Exactly 3 rolls. So pause this video. See if you could just use what you know about probabilities to calculate that. So if you're going to roll 3 times, you're going to have 3 sets of parentheses, 1 for each roll. And if it's going to take exactly 3 rolls, that means you have to fail on the first one, fail on the second one, and then finally succeed on the third one. So failing would be 5/6 that you don't get doubles, and then 5/6 that you don't get doubles, and then finally you succeed 1/6. Multiplying that, we would get, looks like, if my math is right, about 12%. So 12% of the time, it will take you exactly 3 rolls to get out of jail. This question also asks, what about exactly 4 rolls? Well, if I can use the magic of technology and erase some of this, exactly 4 rolls would be failing on the third and then finally having a success on the 4th roll. So that would be this, which we could write, if you want to do a little math and simplify, 5/6 to the third, 1/6 to the first. And whatever that is would be your probability that it takes 4 rolls to get out of jail exactly 4 instead of exactly 3. How about you pause this video and see if you could answer question B, find the probability that it takes at most 3 rolls to get out of jail. At most 3 rolls. So I don't know about you, but I like to write words out sometimes. I know we typically don't like words in math class, but probability of at most 3 is the same as 1 or 2 or 3 rolls. So we need to find what's the probability we get out of jail on the first roll. The first roll, well, there's a 1/6 chance of getting out on the first roll. And an OR probability is addition. Probability we get out on the second roll would be failing the first time, but then succeeding. Failure leads to success. Let's hear it for the 8 keys of excellence. And then the probability of 3 rolls to get out of jail would be failing the first, failing the second, and finally succeeding on the third. Adding those, we would get approximately, if my calculation's right, 42.1%, or a probability of 0.421. So next time you're playing Monopoly, now you can know, should I wait? What are my chances of getting out of jail within the 3 rolls according to the rule book before I have to pay $50? It's a little less than half of the time you will get out of jail just by rolling doubles. So turning the page, let's summarize. The Monopoly example we just did is an illustration of a geometric random variable, and I will break out my highlighter. Bam! Geometric. No, it doesn't have to do anything with geometry, but it does have to do with what you studied in Math 3 and Math 4, geometric sequences or geometric series. Those are related, but we really don't talk about that because this is stats class. So what is a geometric random variable? Well, a geometric setting occurs when we have independent trials of some chance process, my handwriting's even worse on the iPad, and we're recording the number of trials it takes until we get a success. And the until is the most important part. Until we get a success. That is, oh boy, that's a success, okay? What are possible values of a geometric random variable? For a binomial random variable, we could have 1 to n, our sample size. But with a for a binomial, we could have 0 to n, 0 successes to n successes. But with a geometric random variable, we can't have 0. We can't have a case where it took us 0 times to get doubles to get out of jail in Monopoly. That doesn't make any sense. So you could have 1 to, technically, it could take a long, long time depending on what your probability of success is. So the values of the variable are 1 to whenever it ends. What are the parameters of a geometric distribution? Well, with a binary distribution, we had 2 parameters, n, our fixed number of trials, and p, the probability of success. With a geometric distribution, we only need to know the probability of success. So this is a good example. If you're asked a question and you're only given a probability of success, and it asks when might be the first success or some until, those are big, big clues that, oh, this is a geometric setting. Some other ways to tell that it's a geometric setting are these 4 conditions, and they should sound very similar. B, it should be binary. There should be failure and success. So I'll just do S or F. Failure or success. Just two outcomes. Doubles or not doubles. They should be independent events like die rolling. Independent events. And notice the little space I'm going to skip. There should be a constant probability of success. Constant success probability. However, now this is looking like it's going to be bins, if you know what I mean. But it's not bins because there is no n, no fixed number of trials. So instead, we just do t, and we call it bits. Chomping at the bits. So we just need to know if the question is asking how many trials before the first success. How many trials before first success. That's really the main indicator that it's a geometric setting and not a binomial setting. So before the first success. So in general, how can we calculate binomial probabilities? Well, I really don't have the formula memorized. I just do what we did with the Monopoly case. So if you want to know probability of getting a success on the fourth one, I would just say, like, well, you have to fail, 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 and then succeed. And then I would just calculate those. So the formula would be, let's see, you would have, the formula would be your probability of failure, and then you're going to have a probability of success, and you have k failures. So I guess if you want to memorize another formula, you can memorize that. But as you can tell, I really don't have this formula memorized. I just do it this way. Just treat them as independent probabilities, independent events that you're multiplying. And this formula is not on the formula sheet. But again, you can definitely survive without memorizing this formula, as long as you understand this basic idea of you're going to fail until you get your first success. If it's the first success is on the 10th, then you're just going to fail 9 times and then succeed on the 10th one. We can also calculate an average for a geometric distribution. So on average, how many rolls should it take to escape jail in Monopoly? Well, let's not make this too complicated. If the probability of getting out or of rolling doubles is 1 out of 6, then we should expect, on average, we should expect about 6 rolls to get out of jail. Now, it's not guaranteed on the 6th roll you have to get out, but in a large set of rolls, we would expect it takes 6 rolls on average to get out of jail. So in general, we can calculate the mean of a geometric variable as the reciprocal of the probability, which I think is pretty slick. 1 over p, or in our example we just saw, 1 over 1/6 is 6 rolls. So if your probability of getting out of jail is 1/10, the average would be 10 rolls to get out of jail. Is this formula on the formula sheet? No, it is not on the formula sheet. Probably don't really need this formula either, but it is there, and hopefully it makes sense. And you don't really need to memorize the formula. So the next question we're asked, what is the probability that it takes longer than average to escape jail? Longer than average would be more than 6. Right? The average is 6. So longer than average, we actually have an issue here because that could be basically asking, what are the chances that you have to roll 7 or 8 or 9 times, or maybe 10 or 11, maybe 12, maybe 100 times, maybe, uh-oh. There's a problem here with geometric distributions. I guess theoretically it could take you 100 rolls. You'd be very unlucky. You're just rotting in jail, I guess. It would take you 100 rolls to get out of jail. That'd be a very boring board game. I guess you'd be safe from my dad's hotels everywhere. But there must be an easier way to calculate this probability. Really what we need to do is let's do the complement. The complement of all of these is a lot fewer. The complement would be 1 or 2, 3 or 4, 5 or 6. That would be the probabilities that we'll have to calculate. The probability that it takes us 1, 2, 3, 4, 5, 6. So the probability we get out the first time, first roll, is that. The second roll is that. The third roll is that. The fourth roll is that. So that's 4. We have to go to 6. Maybe I'll fit one more down here. 5, 6. Oh, wait. We could just do an exponent. Wouldn't that be nice? 5/6 to the 4, 1/6 to the first. And then lastly, we would have, so that's probably 1, 2, 3 rolls, 4 rolls, 5 rolls. So 6 rolls. That would be 5/6 to the 5th times 1/6. And we would add all of these. So that, plus that, plus that, plus that, plus that, plus that, and add that onto. And that would be the probability. I will give you the incredible, priceless joy of calculating that probability and then discussing with your neighbor, what do you think this probability tells you about the shape of the distribution? Is it left skewed, right skewed, or roughly symmetric? On the next page, this last question is not related to geometric probabilities. It's a review question. So I would like you to read the paragraph and answer question A, B, and C. When I return, I will show you each answer individually, and you can check your work. So pause this video. So for question A, notice it's only approximately binomial. It is binary, check, because people either agree or disagree. There's your two options. That's binary, agree or disagree. There are a fixed number of trials, check. You have 2,500. And we do have a probability of success that we're told right here, 60%. But that's kind of an assumption. Because right when you select someone from this population, your probability of success changes because you're sampling without replacement. Anytime you're sampling without replacement, it cannot truly be binomial. However, there's a condition that we can check. As long as our population is large enough, or as long as the population is 10 times bigger than our sample, then this whole issue of with or without replacement, we can just approximate the answer with a binomial distribution. So the population of the United States is definitely bigger than 2,500 times 10. So I think it's safe to assume that the population of the U.S. is greater than 25,000. So even though it's truly not independent and truly not a probability of success that's constant, we can ignore that issue of sampling without replacement, because our population is so huge, taking one person out of the population isn't really going to affect this overall percentage really much at all. So that is how you discuss and answer question A. For question B, check the conditions for using a normal approximation. Our conditions to use the normal approximation is as long as the number of successes, n times p, and the number of failures, n times 1 minus p, is greater than or equal to 10. As long as those are both greater than or equal to 10, then we would have a normal approximation. So 2500 times 0.6, that's definitely greater than or equal to 10. And so is its complement, 2500 times 0.4. So since both of these are greater than or equal to 10, we would say we can use a roughly normal or a normal approximation in this setting. So then lastly on letter C, use a normal approximation to estimate the probability that 15, 20, or more of the sample agree. So to do this, we need the mean and we need the standard deviation. This is where it gets tricky because you read the question and you say, well, there is no mean given, and well, there is no standard deviation given. But remember, we're treating it as a binomial variable. The mean of a binomial variable is n times p. The standard deviation of a binomial variable is n. Whoops, that's not an n. N times p times 1 minus p. And we know the shape because in part B we just calculated the shape of the distribution. The shape we're saying is roughly normal. So with my handy dandy calculator, 2500 times 0.6, that's a mean of 1500. The standard deviation we would get is about 24.5. So my probability that we're at 1520, that's within one standard deviation, 1520 is my boundary, or more would be shading all under here. And to find the area or the probability of that happening, we would use normal CDF. Remember to label the normal CDF option. Also remember, since I like to review this as a test prep for the AP exam, if you wanted to write it in notation, you would change to a z-score. The probability the z-score is greater than 1520 minus 1500 over that standard deviation of approximately 24.5, which would give us the answer of 20.7%, 0.207. Now that's an approximation to the answer. Remember, we approximately used the binomial variable, and then we used a normal approximation. So we have two approximations here. But this answer will be very close to the actual answer if we didn't use a normal approximation. We could have used a not normal approximation. So let me show you, I didn't ask you to do that here, but let me show you what that would look like using binom CDF. As a binomial probability, we could do the binomial theorem and say, let's do 2500, choose 1520, times 0.6 to the 1520, times failure to the, what was that, 980, and then plus, and we can keep doing that until we get to the very last person, 2500, choose 2500, 0.6 to 2500, and the next one's going to equal 0. Raise to the 0. Now we could do that. I really don't want to have to do, let's see, how many terms would this be? This would be 980 terms. This dot dot dot's rather deceptive. There's 980 terms, or 978 terms in that dot dot dot. We can use a calculator to get the answer much faster. So on the calculator, we can use binom CDF. Some calculators will let you do an upper and lower bound, and I am jealous if you have a calculator like that. Binom CDF goes from 0 up to the number that you tell it. But we want to go 1520 or more. So we're going to need to do the complement, 1 minus binom CDF. And the number we tell it is 1 less than this value that we want, because we're going to calculate up to 1519. So with binom CDF, we would have the number of trials. There's 2,500 adults in our sample, N. Our probability of success is 0.6. And then this value for X or K, whatever you want to call it, number of successes, we would have to put 1519 there. Because again, it's going from 0 up to 1519, and then we have to be smart enough to use the complement so we can actually get the correct side, or the correct tail, of the probability we're looking for. So in my calculator, I've done that, and I do 1 minus that answer. We get this answer when we do binom CDF. I believe, if I remember, our original answer was something, I don't know, something like that, I forget. But notice, if that was our original answer, we're only about 0.5% off. And rather than doing this binom CDF operation, we used a normal approximation to approximate that. And there's actually ways to get even closer with a normal approximation. So if you're kind of upset that we were like, that's too much for you, that's too far away to be accurate, there are other approaches called the continuity correction factor, or continuity correction, which is not part of the AP Stats curriculum, but that can be used to get even closer and better estimates. So to summarize, something that's important, if we go to the bottom of the page, when can we use a continuous normal distribution to approximate a discrete binomial distribution? And that was our conditions n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. If these are true, then you will have a roughly normal distribution, and you can use that normal curve to approximate that. On the next page, and the last page, I have a little proof here to explain where the 10 comes from that we had just written. NP is greater than 10, and 1 minus p is greater than 10. Where that 10 comes from, but rather than make this video longer than it already is, I will save that for another day, and you can begin your homework. You have, at least in 2017, when you're watching this video, you have a packet that's on Schoology. You can write your answers on a piece of paper. And you also have some textbook work, so you can use the rest of class. If there's any left, you can do one of those assignments. Thank you for your attention, and have a wonderful day.